All right. Hello everyone, welcome back to class. Today we are going to be looking at the topic atomic theory, as you can see it. And the first thing we are going to be looking at in this class is how to define atom, molecules, and ions. The definition of atom, molecules, and ions. Now, what is an atom? Now, basically, I can define an atom as the smallest particle of an element that can take part in chemical reaction. Atom was actually coined from the name atomos, which means indivisible. But if you look at it from the view of John Dalton's, which is from John Dalton's atomic theory, which we get to later, it says that matter is made up of small indivisible particle called atom. Now, it was coming from the name. But actually, in today's chemistry, we have discovered that atom has some subparticles inside it. So if you open an atom, we have the nucleus, and inside the nucleus we have some particles there, which you are seeing there, like the proton, the neutron, and electron revolve around the nucleus from the Bohr's model of an atom. Now, a molecule of a compound or element is defined as the smallest particle of that chemical compound or that element which is capable of independent existence. Why an ion is an electrically charged atom. So an atom that has electric charge is what we call ion. We have two of them. We have the cation and the anion. Now, you can either be positively charged or negatively charged. From charge electricity, static electricity, we have two forms of charge, positive and negative charge. So when an atom of an element possesses this charge, which is either positive or negative, we call it an ion. That's what we call it. So we can either have a cation or anion. Now, anion has a negative charge, while a cation has a positive charge. We look at that later, maybe when we are doing other topics related to that. Then, inside an atom, we have some subatomic particles that are proton, neutron, and electron. Now, the proton and neutron are located in the nucleus based on the Bohr's model of atom. Yes, Bohr's model. And the electron is located at something like a spot which orbits around the nucleus in a well-defined cycle or orbit or shear. This is a typical structure of an atom according to the Bohr's model. And this is another typical structure of an atom according to Bohr's model. So, just as you can see, the proton and the neutron are located at the center, which is the nucleus, while electrons are constantly revolving around it in orbit or shear. So this the structure of an atom according to Bohr's. All right. The discovery of electron, proton, and neutrons are as follows by the following scientists. The proton was discovered by Niels Rutherford in 1909. Neutron by James Chadwick by 1932. The electron discovered by J.J. Thomson by 1897. So please take note of that. It's very important. Atomic number is defined as the numbers of proton located in the nucleus of an atom. So the total number of proton of an atom or of an element is equal to the atomic number. So atomic number, an element that has atomic number of 10 will have 10 protons. That's what I mean. If the atomic number is 30, we have 30 protons. Take note of that. Why mass number? Look at another number here. We call it mass number. Now, mass number is the sum of atomic number and the neutron number, or the number of proton and number of neutron. That's what we mean by mass number. E.g., take note, mass number means proton number plus neutron numbers. That's why we say protons plus neutrons. So you add your proton to your neutron. Let's say we have, okay, let's say e.g., element S has the following properties: proton number 1, neutron number 0, 1, and 2. Then what will be the mass number of that element X? Now look at the mass number. The mass number is going to be as follows. Since the neutron number is not 1, we have 3 neutron numbers here. We have 0, 1, and 2. Now, if the neutron number is 0, the mass number is going to be 0 plus 1. That is 1. Take note of that. And if the neutron number is 1, the mass number is going to be 1 plus 1. Proton number don't change. Proton number is the atomic number. Proton number means the atomic number, so that will not change. Neutron number can change. Then that will be 1. Then you add 1 plus 1. The mass number will now be 2. Then if the atomic number, okay, if the neutron number now is now 2, then the mass number will become 1 plus 2, which is proton plus neutron, which is 3. Then we'll have this element. The atomic number will be in the downside, then the mass number will be in the upper side. Take note of that. So this describes a phenomenon that we call isotopes. Isotopes. So these elements now that have the same atomic number, check the atomic number of this X, and S are all the same. They are all the same. So since they have the same atomic number but different mass number, we call such elements isotopes. Now, isotopes are just elements with the same atomic number but different mass number. Now, why are they having different mass number? If you look at the element S we just looked at, you discover that the proton number was always 1. Then the neutron number was not changing. The first one was 0, the other one was 1, the next one was 2. So you discover that it is in the difference of their numbers of neutrons. Now, is the neutron number that actually gave us the difference in the mass number. So when the neutron number is not the same, the mass number will actually be altered, because you cannot alter if you change the atomic number from 1 to 2, the name will change. Let's say, for example, now if the atomic number of an element is 1, we call that element hydrogen. Although the different isotopes of hydrogen has different name, where I'm going to show you now.
All right, the following are the isotopes of hydrogen, namely, the hydrogen has 1 as mass number, we call it proton. Then deuterium, hydrogen have mass of 2, that's mass number of 2. Then the last one is the tritium, that has mass number as 3. If you check, all the hydrogen atoms here have 1 proton, which is in the downside of the H. Check all of them, they're having 1 proton, but they are all hydrogen, but they have different names: proton, deuterium, and tritium. So this is a typical example of isotopes. Elements having the same atomic number but different mass number. We have chlorine 35, chlorine 35.5, and so on. As far as the neutron number is not the same, the mass number will be different. So that's how it is.
So this leads us to the John Dalton's atomic theories. Now, what are the John Dalton's atomic theory and how important are they? Do we actually need them? And what are these theories, if I may ask? And are they still valid? So let's look at the John Dalton's atomic theory now to see.
Now, the John Dalton's atomic theory and its modification. The first is that matter is made up of small indivisible particles called atoms. Atoms can, however, now be divided because we now have some subatomic particles, and as you can see, atoms can, however, no longer be regarded as indivisible because, according to Rutherford discovery, atom is made up of 3 main subatomic particles called protons, neutrons, and electrons. Secondly, this theory states that atoms cannot be created nor destroyed. This statement is still acceptable for ordinary chemistry reaction, but the discovery of radioactivity has shown that atoms can be created or destroyed. If you go into some radioactive reactions like nuclear fission and nuclear fusion, you discover that atoms can actually be destroyed or created. So radioactivity or radioactive reaction or nuclear chemistry or nuclear reaction further this second law or theory. Number 3, atoms of the same element are alike in every aspect and differ from atoms of all other elements. But this statement is not true anymore because of the discovery of isotopes. Because the discovery of isotopes contradicts this statement. It has shown that all atoms of an element are not exactly alike in all aspects. I've already showed you the meaning of isotopes. You have some atoms with the same atomic number, but with different mass numbers. Fourthly, atoms of different elements can combine in small or simple whole number ratios to form compound. Atoms of organic compound could be in large whole number ratio. So this statement is not true because of organic chemistry and giant molecules. Those molecules can be formed from large whole number ratios. Now let's look at the theory from this angle again. The theories are as follows. Atoms. All matters are made up of tiny indivisible particles called atoms. All atoms of a specific element are identical in mass, size, and other properties. However, atoms of different elements exhibit different properties and vary in masses and their sizes. Atoms can neither be created nor destroyed. Furthermore, atoms cannot be divided into smaller particles. The next one, atoms of different elements can combine with each other in fixed whole number ratio in order to form compounds. Lastly, atoms can be rearranged, combined, or separated in chemical reaction. Now, from the modification, but the limitations of Dalton's atomic theory as follows. Number 1, it does not amount for subatomic particles, which we already explained that we now have subatomic particles. That means atoms can now be divided. So Dalton's atomic theory stated that atoms were indivisible. However, the discovery of subatomic particles such as protons, neutrons, and electrons disprove this postulate. Then, number 2, it does not account for isotopes, which we have already discussed. As per Dalton's atomic theory, all atoms of an element have identical masses and densities. However, different isotopes of elements have different atomic masses. Examples: hydrogen, deuterium, and tritium, which I've also discussed. Then it does not account for isobars. This theory states that the masses of the atom of two different elements must differ. However, it is possible for two different elements to share the same mass number, such as called isobars. Such atoms are called what? Isobars. Examples are argon 40 and cation 40. Now, let's look at other limitations of this theory. So please don't forget, two different elements with the same mass number but different atomic number are called isobars. Then elements need not combined in simple whole number ratio to form compound. Steady complex organic compounds do not feature simple ratio of constituent atoms. Examples are sugar, sucrose, etc. We have already discussed. The theory does not account for allotropes. The difference in the properties of diamond and graphite, both of which contains only carbon, cannot be explained by Dalton's atomic theories. So you can see the limitations of this theory, although we have discussed it. I just wanted to know it more better.
Now, the next one we're going to look at now is the Bohr's model, or the Niels-Bohr's model of atom. The Niels-Bohr's model of atom. Now, we have different models. We have Niels-Bohr's model, we have wave mechanics model, quantum mechanics model, and so on. Now, the first one we're going to be looking at now is this Niels-Bohr's. Now, what actually is this model of an atom talking about? You can see the Bohr's model of atom. What is it actually saying?
Postulate of Bohr's model of an atom. In an atom, electron negatively charged, which we have already explained, revolve around the positively charged nucleus in a definite circular path called orbits or shear. Each orbit or shear has a fixed energy, and these circular orbits are known as orbital shears. So this is a type of theory or model that is just trying to describe an atom as a circular shape in which the nucleus that takes the center of the cycle to contain the protons and the neutron, and electrons will now be moving around the nucleus in a form of well-defined cycle or orbits, or like a shear. So it's just like that. You can imagine it. Some of the diagrams of this Bohr's model will be showed now, so that you see what we are trying to say.
As you can see, this is the structure of an atom, typically from one model of an atom. You can see the nucleus, which is comprised of the protons and neutrons, and you can see the electrons, which is negatively charged, revolving around it in orbit or shear. You can see the neutrons has no charge, but the protons are positively charged, while the electrons are negatively charged. Now, the following are some of the limitations of the Bohr's model of atom. Now, the first thing is that it fails to explain the effect of magnetic field on the atom spectrum and the effect of electric field on the atom spectrum. Also fails to explain the atomic spectra of large atoms. Now, let's look at the wave mechanics model. Which is the quantum mechanics. Now, the next one we are having here is the quantum mechanics, or the wave mechanics model. Now, the wave mechanics model theory proposes that each electron's cycling and orbital nucleus occupies specific energy, specific orbitals, and spin is certain direction. But the orbitals is like a cloud or wave of energy, not the ring you might be imagining, thinking about the Earth's orbit around the sun. Now, what this wave mechanics model is actually saying is electrons do behave like a wave particle. It's not just like an actual particle, but behave like a wave. That is where the wave mechanics is coming from. It behaves like it exists in an electron cloud. It's not moving in a definite path around the nucleus of an atom, just like the one from the Bohr's model that states that electrons do move in a ring, or do move in a shear, or do orbit around the nucleus of an atom. No, but the wave mechanics model is trying to tell us that electrons are like just wave particles to our nature. They are discrete particles. Now, what is the meaning of quantum mechanics, or quantum model. Although the quantum model is much harder to understand than the Bohr's model, it accurately explains the observation regarding the large or complex atoms. Quantum model is based on quantum theory. According to the quantum theory, an electron has particle wave duality, and it is impossible to locate the exact position. That's what I was trying to explain before. So to explain to locate the exact position of the electron, that is uncertainty principle. Thus, this model is mainly based on probability of an electron to be located anywhere in the orbital. It also states that the orbitals are not always spherical. The orbitals have particular shapes. Remember, we have s orbital, p orbital, d orbital, and so on. Particular shape from different energy level and are 3D structures. Now, let's look at more on this theory. Now, so many scientists work on this theory, like de Broglie, Eric Schrödinger, which form the wave function equation. Although we will not be looking at, because we are not looking at wave mechanism model in this class. We are looking at atomic theory. So maybe we'll have a class on wave mechanism model. We'll explain the meaning of wave mechanism model, the scientists that works on these wave mechanism models. Now let's look at more things about this model.
Now, from here, you will see that the major difference between this Bohr's model of atom and the wave mechanism model is that the Bohr's model of atom theorized that electrons orbit an atomic nucleus in a well-defined circular orbit. But the wave mechanism model theorized that instead of well-defined circular orbit, electrons orbit an atomic nucleus in clouds, and the electrons within the cloud behave like a wave instead of just like a single electron. Take note of that. Very, very important. Very, very important.
Now we are going to be looking at now orbital representation. And what's the meaning of orbitals? Now, the wave mechanism model leads us to something phenomenal we call an orbital. Now, what do we mean by an orbital? An orbital is just the probability of finding an electron in the volume of space. And we have the SPDF orbital. S denotes a sharp spectrum. P denotes the principal orbital, which can be degenerated to 2px, 2py, 2pz. We also have 3ps, 3py, 3pz. We can degenerate. Now, there's something we call degenerate orbitals. We have atomic orbitals, molecular orbitals, degenerate orbitals. Degenerate orbitals means orbitals with the same energy level, equal energy level. And you can see we have x orbital here. We have p orbitals. There's something we call p orbital. This x denotes something sharp. Then this p denotes something principal. Then the d denotes something diffuse. We have d orbitals. Then the f denotes something fundamental orbitals. Now, x orbitals is spherical in shape. Spherical in shape and can occupy maximum of, or can take maximum of 2 electrons. While the p orbital is dumbbell in shape. And can occupy a maximum of 6 electrons. The p orbital, the d orbital is double dumbbell somehow and can occupy maximum electron of 10 electrons, while the f orbital, the complex shape, can occupy a maximum of 14 electrons. Now, there are some other important things about this SPDF orbital which we may not be looking at in this class, because we are just doing introduction to the course. But take note of the x cannot be degenerate. It's only PDF. You can subdivided into equal parts based on the Pauli's exclusion principle that no more than 2 electrons can occupy a single orbital. And if they do, they might spin in opposite direction. That will lead us to these quantum numbers. Now, what is the meaning of quantum number? Let's quickly look at that.
Now, it said quantum number are sets of numbers used to describe the positional energy of electron in an atom. And we have 4 quantum numbers, namely the principal, azimuthal, magnetic, and spin quantum numbers. So,
the set of numbers used if you want to describe the position and energy of the electron and atom, we use the quantum numbers. And you can see we have the principal quantum number, we have the azimuthal, we have the magnetic, and the spin quantum. Now, the principal quantum number has a symbol, small letter n. Then the azimuthal, which is also known as the angular momentum quantum number, has the symbol L, that is small letter L. Then the magnetic quantum number has the symbol M subscript L. And this electron spin quantum number, we call it spin quantum number, has the symbol M subscript X. So note these symbols because in most cases what you'll be seeing will be their symbols, not actually their names. So anywhere you see N, it denotes the principal quantum number. Then L denotes azimuthal or angular momentum quantum number. Then M subscript L denotes magnetic quantum number, and the M subscript S denote the electron spin quantum number. Now, the principal quantum number denote the mean energy level of an atom, denote the energy level of an atom, while the angular momentum describe the shape of electron cloud, and the magnetic quantum number give the orientation of orbitals in space, and the spin quantum number give the orientation of electron spin in space. So know their respective definition is still very, very important. So now let's try and get their integral values. The integral value of N, L, M subscript L, and M subscript H. So see what we're going to have. Now from this, we have the principal quantum number with integral values, which N denotes principal quantum number, L denotes the azimuthal quantum number, the ML denote the magnetic quantum number, the MX denote the spin quantum number. Now the integral values of N are from 1 and above, 1, 2, 3, 4 and above. Then while L start from 0 and end at N minus 1. Now N denote principal quantum number. Now this N you are seeing here means principal quantum number, and look at this, N and this N are the same thing. So N start from 1, 2, 3, 4 and so on, while our L starts from 0 and end at N minus 1. So therefore, okay, let's keep on going because I'm going to explain a lot of these things here. Now we have ML. ML means magnetic quantum number. That this is a symbol for magnetic quantum number, and the integral values range from minus L to plus L. Now, which one is minus L again? Minus L is the azimuthal quantum number. And if I say something like, okay, from now we have if N is equals to 1, what will be the value of L at N is equals to 1? The value of L will be, now remember, value of L must start from 0 and end at N minus 1. Now N is 1 here. What is 1 minus 1? 0. So we end at this starting point. So L will be 0. And ML must range from minus L to plus L. So ML will also be, you cannot move from minus 0 to plus 0 because minus 0 to plus 0 is still 0. So ML will becomes 0. So at the principal number is equal to 1, our azimuthal will be 0 and the magnetic quantum number is 0. Take note of that. Now, the spin quantum number has two permissible integral value, which is the minus half to plus half. The minus half means spinning downward, while the plus half means spinning upward. Now, let's look at some few examples under these quantum numbers so that you see what I'm trying. Now, let's say if our L is equals to 2. Remember, what is made of L? L means the azimuthal quantum number. Now, if our L is equals to 2, our MM must range from minus L to what? Plus L. That's from minus 2 to plus 2 now. Now, if you want to move from minus 2 to plus 2, you're going to have minus 2, minus 1, 0, 1, 2. And if, look at another question, if our N is equals to 2, what will be ML? Now, to get the integral values, now we are going to have some numbers of integral values. Now, if we want to use a short formula to get it, our ml will just be principal quantum number raised to power 2. So magnetic quantum number is equals to principal quantum number raised to power 2. Now, if n is 2, our ml will be n squared, which is 4. We're going to have 4 integral values. Now, let's see, and let's try and see if it is possible, or if we can get the 4 integral values out, or let's see if we are correct. Now, if n is equal to 2, L must be 0 to, remember, 0 to 2 minus 1 is 1. So we're going to have 0 and 1 for L. Now, at L is equal to 0, ML is equal to 0. I've already explained that. Then at L is equals to 1, ML will be from minus 1 to plus 1. That is 1 minus 1, 0 plus 1. So how many integral values are we now having for ML now? We're having 0, which is 1, then 2, 3, 4 integral values, which corresponds to this 4 that is here. So please take note of that. It's very, very important. So let's look at one more. Let's look at more questions on this. Now, if our L is equals to 3, what will be our ML? You can even do that now. Our ML will read from minus L to plus L. That is from minus 3 to plus 3. So I'm going to have this integral value for ML. If our N is equals to 3, or if N is equals to 4, what will be the value of ML? What will be the value of ML? If N is equal to 3, ML will be 3 squared, 9 integral values. So you are going to try your best now. Try and list out these 9 integral values. So check if you can get them. Just do it. If N is equal to, let me just explain this one now so that you see it. I did not do it because I wanted to do this one at classwork. If N is equal to 3, L will be 0, 1, 2. So you get the ML for 0, get the ML at for L is equals to 2, L is equal to 1, which is from 0 minus 1 to plus 1. Get the ML for L is equals to 3 and 2, is from minus 2 to plus 2. So I'm going to have 9 integral values total. If N is equals to 4, what will be ML? The integral values is going to be 16 integral values. Try and write that out. Now, there's something also called electron share capacity. Electron share. Now, electron share can be the KLM shares, and the formula to get the capacity in which this KLM can take is given by 2n raised to power 2, where n is the electron share number, or it is synonymous actually to the principal quantum number. So this KLMN is somehow like the principal quantum number, or it corresponds to the principal quantum number for n. Now that means at K, where do principal quantum number start from? Started from 1. N started from 1, 2, 3, 4, and so on. So the same thing in this share, electron share now, K, N will start from 1 for K. So if for K now, N is 1, for L, N is 2, for M, N is 3, for N, N is 4, and so on. So for example now, how many electrons do we have in the M share of an atom? So how many electrons are we going to have in the M share of an atom? For M, we are going to have 1, 2, 3, N will be 3, N will be 3. So we put 3 here. 3 squared is 9. 9 times 2 give us 18 electrons. That's why we're going to have 18 electrons.
Alright, you can see the shares of an atoms, electron share, and atoms, and as they are different energy level or orbit. And you can see the K share, the L share, the M share, the N share, the O share, and the respective values of N and the respective values of electrons that can be found in that share. You can see for the K share 2 electrons, L share 8 electrons, M share, which we calculated before, 18 electrons. Then the N share 32, then O share 50 electrons. So this one is very, very clear now. So let's move to the next one.
On electron share, you can see the formula is 2n squared. We define the total electrons in the share. The orbital number, which corresponds to the principal quantum number, which is n here, is 1, 2, 3, 4, etc. and so on. For K, n is 1. For L, n is 2. I've already explained that. You can see the answers here.
Now let's look at the principles of distributing electrons in orbitals. Principle of distributing electrons in orbitals. And the first principle I'm going to look at now is the Aufbau principle. Now, in this principle, it states that electrons are distributed or shared in orbitals in order of increasing energy level. So if you want to share or distribute electron in orbitals, you have to do it in order of what? Increasing in it or increasing energy level. Now, this principle can best be explained by this arrangement of our orbitals. Now, we have 1x, 2s, 3s, 4s, 5s, 6x. Then the 2 starts from p. So p starts from 2. P does not start from 1. So we have 2p, 3p, 4p, 5p, 6p, and so on. We have 3d, 3. So d starts from 3. Then and so on. So remember, at our n is equals to 1, I don't want to use the principal quantum number to be explaining this so that it will not look complex. At n is equals to 1, our m azimuthal quantum number will be 1, 0, just 1 integral values. As n is equals to 2, we have 0 and 1, which is 2 integral values. As n is equals to 3, we have 0, which is also the same thing, and so on. So just verify right, you start from s start from 1, p start from 2, d start from 3, f start from 4. So you ended at f. We have s, p, d, f. So we have 1s and so on till as we go to the last element, then 2p, get to the last element, 3d, then 4f. Now, if you want to share the electron, you have to do it this way. You have 1x first, we have 2x, 2p, 3s, 3p, 4x, 3d, 4p, 5x, 4d, 5p, 6x, 4f, 5d, 6p, 7x, and so on. That's how it is done. So that's what they are saying here, etc, and so on. E.g., if we have oxygen with atomic or proton or number of electron, this is the number of electron. Okay, we have oxygen, which is just neutral oxygen, we has 8 electron. I want to write the atomic configuration. Now we are going to have 1s2. I told you before, you can have s can take maximum of 2, p can take maximum of 6, then d can take maximum of what? 10, f can take maximum of what? 14. So we have 1s2, 2s2, then 2p4. We're going to have 1, that is 4, 8. We have 8 electrons. So as simple as that.
So this diagram clearly explains this Aufbau principle. For example, you have 1x, 2s. S orbital starts from 1. Then the p orbital starts from 2. D orbital starts from 3. Then f orbital starts from 4. So you can see how the lines are moving from 1s, 2x, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6x, 4f, 5d, 6p, 7s, 5f, 6d, 7p. They will move to 8x. You can see how it's moving. So that is how we run the Aufbau principle. So please take note. It's very, very important. Very, very important. Now, as you can see, these are electronic configuration of some atoms and their ions. Remember, cations means positively charged ion, while anion means negatively charged ion. Now, the first I'm having here is Na, which is sodium, which you have done. And look, you can see the electronic configuration 1s2, 2s2, 2p6, 3x1. That is for sodium. What about sodium ion, which is actually a cation? Now, for sodium to be something like being in its ionic state, it's going to lose 1 electron. It's going to have Na plus. NH plus. So if it loses 1 electron, then this 3s1 will not be there again. So the electronic configuration of sodium ion, which is Na plus, will be 1s2, 2s2, then 2p6. The same thing with this phosphorus and trianion. But for phosphorus, the electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p3, which will give us a total of 15 electrons. But for it to form an ion, it's going to gain 3 electrons to obtain its octet state, or to have 8 electrons in the atomic shell. You need to gain 3 electrons. So if you gain 3 electrons, Then we're going to have P3 minus. So we're going to have T and P3 minus. So because of this, we are going to add 3 electrons to the initial phosphorus we are having. If you want to write for phosphorus ion, then we will be having 1s2. Remember, if something gains electron, it's going to take a negative sign. The charge, the ionic state, if it gains electron, will take a negative sign. If it loses electron, it's going to take positive sign. Take note of that. Then we're going to have for phosphorus ion now, which is P3 minus, will be add 3 to that first one, the normal neutral phosphorus we have, which is now give us 1s2, 2s2, 2 pixies, 3s2, 3 pixies. For the aluminium atom, we're going to have the configuration, which is 1s2, 2s2, 2 pieces, 3s2, 3p1. But the aluminium dication, this is losing 2 electrons. This aluminium is losing 2 electrons, which is La2 plus. Then if you remove 2 electrons from this 3x and 3p orbitals, you're going to have 3s1 left. Remove one from that 3p, there will not be there again. Then if you remove one from this 3s2, only one will be left there. So that's what you're going to have. But for the other aluminium, the main aluminium ion, which is aluminium Al3 plus, the configuration will be, if it is Al3 plus or plus 3, then you're going to have the configuration 1s2, 2s2, 2p6, 3s1. Now the 3s1 will not be there again. So the thing will just end at 2p6. You're going to have 1s2, 2s2, 2p6 for Al3 plus. Now this one you're seeing here is for Al2 plus. Now let's go to the last one, Fe, which is ion. Now for the normal ion, you're going to have 1s2, 2x2, 2p6, 3x2, 3p6, 4s2, 3d6. Now for aluminium 2 ion, which is Fe2 plus, we lose 2 electrons. Now if we want to remove this electron from this aluminium, since it's a transition metal, because remember aluminium is a transition element, and it has this d orbital feed up. So what we'll do, we'll remove the electrons to form ion. Now we're going to remove the electrons from the 4s. So we're going to remove the electrons from the 4x, which we have, we'll now be having 1s2, 2s2, 2p6, 3s2, 3p6, then 3d6. The 4s2 will be removed since it's losing 2 electrons. So please take note of that, in case you are writing ionic states of transition elements, so that you will know what to do. So assuming you are doing aluminium 3 ion now, which is Fe3. Now since there's no any other 4s again, then you now start removing from that 3d. So I will give you this assignment now. Go and look for the electronic configuration. Go look at the electronic configuration of aluminium 3 ion and copper ion. Yeah, also look at that. So thank you.
So what about sodium, which is having 11 electrons? How we're going to distribute them? We're going to have start from 1s2, 2s2. Remember 1s, 2s, 2p, 3s, 3p, then 4s, 3d, and so on. Remember the principle, Aufbau principle. Then we're going to have 1s2, 2s2, 3p6, then 3s1. Then we go to get to 11, then you stop. Calcium, 20 electrons. We have 1s2 and so on, which we have 20 here. Then what about calcium 2 plus? This calcium ion, this calcium have lost 2 electrons. So if the neutral calcium, remember we discussed ion at the beginning of this class. Remember? So this C8 plus 2 now means calcium ion, means you have lost something like 2 electrons. Or giving out 2 electrons. So if this calcium that is having 20 electrons gave out 2, then we have 18 left. So you just distribute that 18 accordingly. So remove 2 from this normal neutral carbon now, we're going to have remove this 2 electron that is here to the one before us again. We're going to have at 3p6. That's what we are going to have there. So we also have the Pauli's exclusion principle, which states that no more than 2 electrons can occupy an orbital, and if they do, they should spin in opposite direction. Then we have the Hund's rule. Hund's rule says that electrons are distributed in orbitals singly before pairing. Singly before what? Pairing. Now let's go at the carbon atom. Carbon atom. Now, carbon atom has 6 electrons, and we want to distribute them in orbitals. Remember we have 1s2, 2s2, then 2p6. And Pauli's exclusion principle said no more than 2 electrons can occupy a single space in an orbital. So these 2 pieces now we are going to degenerate it into px, py, pz, in which ps will take 2, py will take 2, pz will take 2. Because this p orbital that have 6 electrons now, we distribute them something like in terms of, we degenerate that p orbital into parts, so that the 6 electron will not stay in one single space. 2, 2, 2 will stay in their space, because no more than 2 electrons can occupy a single orbital according to Pauli's exclusion principle. So for the 1s2, one spin up, the other one is spinning downward. Same thing for this. But for this one that has 6 electrons, now if you therefore distribute the electrons here singly before you start pressing. So if you have 1, 2, but there's no other electron again, so we just have 1 and 2 here. And if you check this compound now, if you get this atom now, we have 2 unpaired electrons here. Electrons that are not paired, we have 2 of them, 1 and 2. So we have 2 unpaired electrons there. And you can also ask how many of electrons do we have in oxygen. You can also write that one out.
Alright, you can see the electronic configuration of nitrogen, oxygen, fluorine, and neon. You can see how many unpaired electrons we have in nitrogen, numbers of unpaired electrons in oxygens, fluorine, and neon. Okay, typically, elements with unpaired electrons are said to be paramagnetic, while those with paired electrons all through are said to be diamagnetic. So you can take note of that. I can ask you which of these elements is diamagnetic. In this place now, the diamagnetic element, according to how their electrons are paired, is this neon atom, because all the orbitals are being fed off, or all the electrons in the orbitals are paired. So the one with unpaired electrons like nitrogen, oxygen, and fluorine are paramagnetic because they have unpaired electrons. Yeah. Now this is the sodium atom, which has 11 electrons. So you can see 2 is already. We have 2 of them here. The first one, which has the red sign, is bad. That means it's not correct. Then the second one is good. Why is it good? Now let's explain. Now the innermost shell take 2 electrons. You can check the innermost shell. This first one is taking all the electrons, which is not right. Now the second one, the innermost shell took 2 electrons. Then the next shell, which is the outer shell, then the outer one is having 1, but after that innermost shell having 2, the rest will be having 8. Check the next one. That one is having 8. Then the other one is having 1, because we have 11 electrons to share. So if the innermost shell is having the inner shell is having 2, then the next one is having 8. That's already 10 plus 1 that is left. That will give us 11 electrons. So if it loses that one now, we are going to have the innermost shell, which will be 8 electron, which is completely filled up. So it will form sodium ion by losing 1 electron. So you can also use this configuration to check how the ion of a neutral atom is going to take, the shape is going to take, whether it's going to be plus or minus, or it's going to be plus 2, plus 1, minus 2, minus 1, plus 3, minus 3, and so on. So this can also help to do that, this electronic configuration method. Yeah. The looking at the Bohr's model of structure of atoms, how to configure the first 18 element, that is from hydrogen to argon. You're going to have the following configuration. You can see it. Now the innermost shell do take 2 electrons, maximum 2 electrons, while the outer shell take maximum of 8 electrons. So this is how to configure electron when coming from the Bohr's model of an atom.